All right, so we are now going to talk about isotopes, and isotopes are another revision to Dalton's theory. Dalton thought all atoms of the same element were exactly alike, and we now know this to be incorrect. Isotopes have the same number of protons and different neutrons. So, therefore, if you have an element like iron, all the atoms of iron are not alike. They are alike in that they all have 26 protons, but their neutrons vary, and because their neutrons vary, their average mass is different. And we'll talk about that in a minute. Also, ions, the number of electrons aren't the same. You can pull off or add electrons to make positive or negative ions. Do keep in mind, and I keep stressing this, that protons define the element. It's the number of protons that make the element what it is, and we should have learned that doing the game. So if we look at the periodic table, we will see the atomic number on top, the number of protons, the thing that defines the element. And then here is an average atomic mass. And that is the average if we had a whole bunch of atoms on Earth of this element. So let's talk about what we're talking about there. So hydrogen can exist in three varieties. Hydrogen, by definition, has one proton. So you can see these three varieties all have one proton. However, when it has no neutrons, hydrogen has a mass of 1. When there's one neutron with the proton, hydrogen has a mass of 2. And when there's two neutrons with the proton, hydrogen has a mass of 3. So these are the three isotopes of hydrogen. So um, they all exist as hydrogen. They act, quote unquote, like hydrogen, but because they have different masses, they have because they have different neutrons numbers, they have different masses. So we want to account for this when we're doing the periodic table, right? So here's hydrogen up here. I'm going to do it in an actual color. So the fact that the average mass of all the atoms of hydrogen, if you had them in one place, is 1.008. That's letting you know a couple things. One, that the majority of hydrogen exists as hydrogen 1. But there are some other atoms that are a little heavier that are pushing that atomic mass a little further up. So that is why that average mass does that. So let's look at carbon, a thing known to me. Carbon, by definition, on the periodic table, so carbon should speak to you that it has 6 protons. So there are 6 protons in all forms of carbon. However, the neutrons can change. There can be 6, 7, or 8. The electrons, let's just say for now, we're not that worried about them, but we'll make them all 6, so these are all neutral. But the neutrons are different, therefore the masses of these are different. So this has 6 and 6, so it's carbon 12. This has 6 and 7, a total of 13. And this has 6 and 8, so the mass is 14. And these act in different ways. If we look at this thing we did, right? So here's carbon, it's neutral. It has 6 protons and 6 neutrons. That's one option. There can be 7 neutrons. I just raised the mass here. If you look here, let me move my cursor over here, right? So here's 13 mass. We have one more neutron than proton. That's still carbon. And here's another neutron. That's a mass of 14. So there's 2 more neutrons than protons. That's still carbon because it has 6 protons. So all these exist. But as you will see, if I take one of those off, while the 13 is stable and the 12 is stable, the 14 is not stable. And because it's not stable, what we say is it's radioactive. And radioactive carbon exists, and we all have it in us. And anything we eat with carbon has a little radioactivity. But here's the little bit, what we're talking about when we say a little bit. 98.9% of all carbon is carbon 12, that very stable 6 proton, 6 neutron. A very small portions, 1.1%, is what we call C13 or carbon 13, because it has 6 protons and 7 neutrons. And then even a smaller percent, 1 times 10 to the minus 10. So think about that. That's 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1. That many percent. That's the percentage. Oops. So, percent. All right. um, of carbon that's radioactive. So it's not many carbons in your body that is radioactive, but they do exist. And they are radioactive because they have 6 protons and 8 neutrons. All right, so all these exist, and we need to reflect that in this average atomic mass here that shows up on the periodic table. So we're going to talk about that, but let's talk about this radioactive thing real quick first. We talked about the study that a group did where they took a baggie, right? And in that baggie, there was a tree, or they put a tree around a baggie. I mean, a baggie around a tree. So I'm going to draw a little tree here. There's a tree. And I'm going to have to do purple because there is no brown. All right. So in there, they put this radioactive carbon 14. So um, they took radioactive carbon 14 and they made carbon dioxide out of it. So let's make carbon dioxide there. And then the tree takes that in, right? And then it spits out oxygen. Now, that oxygen is not radioactive. It doesn't have the carbon with it anymore. So that oxygen is free of radioactivity. So all that radioactivity that was in the carbon dioxide that we put into this baggie, so this tree can only have radioactive carbon dioxide, goes into the tree and makes this, makes the stems and the food and the, goes to all the things that the tree needs from photosynthesis. So by putting this tree in a radioactive carbon dioxide environment, we were able to make radioactivity come onto the tree. And that allowed scientists to now trace, because we have ways of tracing radioactivity. We can use Geiger counters or other methods that are more sensitive than that. And we could start looking around the forest and say, where'd the radioactivity go? Because we did this. We made this change happen. The radioactive carbon dioxide was only exposed to one tree. So if any other tree in this forest, and I guess as a control, you can test all the trees before you do this, make sure they don't have radioactivity. And then after a while, what they found is that all the trees had radioactivity. And because of that, they knew that trees share resources. They do it through their roots, it turns out, and it's not a species specific thing. So pine trees don't only share with pine trees, and oak trees don't only share with oak trees. All trees share with all trees. And other things you may have heard of, the carbon dating that happens, if you've ever heard about that. When you stop eating plants that have this little bit of radioactivity in them, not that much because we don't eat plants that have been treated with radioactive carbon. But when you eat anything, and as I told you, there's a little bit of radioactivity in it, you sort of maintain the number of radioactive carbons in your body every time you eat anything that has carbon in it. Well, when you die, you stop eating. And since you stop eating, you stop putting radioactive carbon in you. And therefore, they can use the amount of radioactive carbon that's left in your body to determine how long you've been dead. Now, that only works for, I think, 13,000 years, because after 13,000 years, I think, don't quote me on that. That number sticks in my head for some reason. After a certain amount of time, all the carbon in your body is going to be gone anyway. So it won't be able to tell you how old something is by the millions, but it will be able to tell you how old something is in more recent than that. Phosphorus can also have radioactive isotopes. That's important because DNA has phosphorus in it, so they can make radioactive DNA and then follow that DNA where it goes. So if they want to know what happens when a virus gets into a body, they can make the virus have radioactive DNA and then put the virus into a mouse or whatever and then see where that DNA ends up. Um, anyway, so those are some other things that you can find radioactive. All right, so here's how we do this. We have to figure out the weighted average of the atoms. And the way we do that is we use this equation that the mass of the isotope times the percent of that isotope plus the mass of another isotope times the percent of that isotope is going to give you that average atomic mass that you see on the periodic table. So another way to think about this, let's say we have a school that's only football players um, and ballerinas. It's like a magnet school. So the football players have an average mass, let's say, of like 180 pounds. I don't know if that's accurate or not, but let's say that is. All right. And the ballerinas have an average mass of, I'm going to go with 115 pounds again. don't know how accurate that is, but there's a big difference, right, between the football players and the ballerinas. And let's say we're worried about the floors of the school collapsing if the average weight of a student is closer to 180. Like if we only had football players, the floors of all the buildings would collapse because they can't handle that kind of mass. So that's why we had to add ballerinas. I don't know, making this up as we go. So if we had fifth, or let's say we had 45% football players, and therefore we had 55% ballerinas, this would help us figure out what the average mass of a student in there was. So 180 times 45 plus 115 times 55 would tell us what the average mass of a student is. And based on these numbers, the average mass would tend toward the 115. And I have misplaced my calculator in Studio Roach. So I'm going to just leave you to figure that out. All right. But this is what we did with cereal in the lab. All right. We're just trying to figure out what's the average mass of one atom. All right. We did two different cereals. There was a heavier version, a lighter version. And if the average mass tended toward the heavier version, that means you had more heavy than light. And if it tended toward the lighter version, that means you had more light than heavy. So the same is true with these atoms. If we have a whole bunch of atoms, here's chlorine, for example. So chlorine has two isotopes, chlorine 35. Chlorine, by definition, has 17 protons, so therefore chlorine 35 would have 18 neutrons, and that's 75.78% of all chlorine. And chlorine 37, which has 17 protons and therefore 20 neutrons, and that's 24.22%. So the first thing you need to do here is convert these to percentages, and you do that by moving that decimal over two places. So that's 7578. And this one moves over two places, so that's 0.2422. All right, so that's the first thing you do. And the next thing you do is you take the mass of this one and multiply it by the percentage. So the mass is 35, the percentage is 0.7578. Then you take the mass of the other one, multiply that by its percentage. So the mass of that times 0.2422. And 35 times 0.7578 is 26.52. 37 times 0.2422 is 8.96. And when you add those together, you get 35.48. And if we go back to our periodic table here, you'll see for chlorine, that's pretty close to what chlorine's average mass is, 35.45. So again, we simplify these because you're just learning. That's why 35.48 is pretty close to 35.45. That is how we figure out that number on the periodic table. So we're taking into account that a third of all chlorines are 37 and I'm sorry, not a third, a quarter, right? 25% are chlorine 37 and 3/4 are 35. So if we go back to the Thomson thing and you run a mass spec, this is what a mass spec looks like. It shows you the mass of everything in it, and we shoot chlorine in there. We would get a peak at 35 because that is the mass of the majority of chlorine. And that would give you a peak that's 3 times higher than the peak at 37 because there is 24% that is 37 and there is 75% that is 35. All right, so let's do one with bromine. It is known that bromine comprises of 79, which is 50.54%, and the rest is 81. So the 79 is bromine 79 has 35 protons, therefore 44 neutrons, and that's 50.54% of all bromine. The rest is 81, bromine 81, which is 35 protons and 46 neutrons. We therefore know, since the rest means 100%, right, is what all of bromine is, it would be 100% minus the 50.54% of the first one. So therefore, we're looking at 49.46. We will at first move this decimal over so we have actual decimal numbers, 50454. And we'll move this decimal over two places. So that's 0.4946. And then we're going to plug these numbers in. So it's the mass of the bromine times the percentage plus the mass of the 81 bromine plus its percentage. we're going to multiply 79.5054, and we're going to get 39.92, and we're going to multiply 81 times 0.4946, and we're going to get 40.06, and we add those up, and we get 79.98. So again, if you look at the periodic table, that should give you what it is for bromine. So bromine is right there, 79.90. Okay, it's right there. And that is 79.98. So again, we simplify this for you. There's actually a little more going on here, but just so you can do these problems, we're pretty close though. And again, if we were to do a mass spec of this, we would have a peak at 79 and a peak at 81, and they would be about the same size, with the 79 being a little bit higher because it's 54. It's about a 1-to-1 ratio here between those two. All right. Hopefully that helps. And thanks.